Conductors and insulators. In this video, we'll be looking at electricity behavior based on materials and examples in e-bike systems. Why it matters? Because it's critical knowledge for e-bike electrical problem solving, electrical safety, and key concepts that are used in later videos. Prerequisite VODs, just the one on voltage, current, and resistance. Beginning with superconductors. Going back to our highway analogy, think of a dream highway with virtually no resistance or loss. Electricity flows unimpeded. It only works under extreme conditions, so room temperature superconductors would be ideal once we could invent them, but they're prohibitively expensive and they have to be at almost absolute zero temperatures, so it's not practical for e-bikes. A regular conductor, however, is like a standard highway with normal traffic. Electricity flows normally with low to medium resistance. You'll see this in everyday wires, motors, windings, and pretty much all metals are conductors. A semiconductor is like a standard highway with traffic lights. In a semiconductor, electricity can flow and stop. It's found in virtually every integrated circuit, which you'll see in computers, smartphones, e-bike controllers, and displays. Think of these little black microchips here. And then we have insulators. They're like a completely blocked off highway. They stop electricity from flowing at all. There's very high to infinite resistance, and in everyday life it tends to be wire insulation with most plastics and rubber, like this wire coating here. Now here's a few examples you'll see in the e-bike industry, starting with the most conductive in green, heading down to the least conductive or highest resistance in red. Beginning with copper, you'll see this in a lot of motor windings or wires. It's very cheap, effective, and makes a really good electrical conductor. Followed by aluminium or aluminum, which you normally see on bike frames. Then you have just all other metals, so steel, titanium, all of them, they can conduct electricity. And then you have raw carbon. It's an interesting one because it's a mix of raw carbon fibers and then also resin, which makes up carbon fiber. If you expose the raw carbon itself, it can be pretty conductive, but if there's a coat of resin over it, it can insulate. And then after that, we have water. There's an asterisk there because pure water is not conductive at all, but once you have different minerals and materials mixed in with it, like salt water, for instance, it can become quite conductive. And then there's you. Human skin, at least when it's dry, can be pretty resistant, but once you break that skin barrier or your hand becomes wet, you can conduct electricity pretty easily. And then there's paint. Most paints, unless by design, usually insulate, but most paints are also a very thin coating, so it's easy to get past the paint and get to the raw metal behind it, say for instance on a painted frame. Then you have oils, which is a bit of an interesting one. In e-bikes, mineral oil, which you see in the brake lines, that is actually insulating, but if you had dot fluid, for instance, which is used on like Magura systems, that's a glycol-based liquid, so that's actually conductive. So your oils and lubricants can really depend on what's added into them. And then we have isopropyl alcohol. That's a pretty useful electrical contact cleaner because it insulates. After that, we have polymers. Polymers refer to a group of materials which have a particular molecular structure, things like plastics and a few other things as well. The vast majority of polymers, except a very few, are designed to be insulators. A plastic is something that could be heated and then formed into a shape once cooled. All plastics are polymers, but not all polymers are plastics. An example of one of these polymers, polyvinyl chloride or PVC. You'll see that a lot in things like electrical tape, which is a good insulator. And then rubber or nylon, which you might also see in tires, is also a polymer. And then silicone, not to be confused with silicon. Silicone is a very good insulator that's quite resistant to heat and also electricity, but it can be abraded or chipped away pretty easily. And then finally we have resin. You'll probably see resin most commonly in the industry bound together with carbon to make carbon fiber bike frames. Resin just by itself, not including the carbon, is a fantastic insulator. And here we have a quick video doing a continuity test on conductors and insulators using a multimeter. First of all, we want to set our multimeter to the diode or continuity test mode. On this mode, in this multimeter, 1 represents infinite resistance or insulating, and close to 0 represents very little resistance or conducting. Starting with the nickel strip, which is conducting electricity. Moving on to the resistor, which is conducting mostly, but there is some resistance. Remember, to get an accurate reading, sometimes you have to push down firmly with the multimeter's probes. Now moving on to heat shrink, which is insulating, not conducting electricity at all. And finally, moving on to the stainless steel drink bottle with a faded coat of paint. When probing the steel, we see it's conducting, but when we probe the paint and the steel, we see it's insulating. However, if we push hard through the paint, we reach the conductive layer of steel beneath. It goes to show that thin paint is not a reliable insulator. Click here to watch the next video. It is the best free thing you can do to tell YouTube to support the channel. Otherwise, if you want to do more, check out the links in the description. Thanks for watching.